Okay, so our next 3 lectures will be devoted to topological vector spaces. Topological vector spaces is a large area with many applications in analysis and geometry. Well, we have only 3 lectures, so of course we'll discuss only the very basic facts and results from this theory. In particular, we will see soon that even in classical subjects of functional analysis, in particular in the spectral theory of linear operators on the Hilbert space, some tricks from the theory of topological vector spaces are very useful. In particular, when we construct the Borel functional calculus for a normal operator on Hilbert space, we will extensively use the results, basic results of the theory of topological vector spaces. Okay, so as usual, we work over the field of real numbers or over the field of complex numbers, and we denote by bold K our base field. By definition, a topological vector space is a pair X and tau consisting of vector space X. X is a vector space over K, and tau is a topology. Tau is a topology on X. And we require that these 2 structures, the algebraic structure of vector space and the topology, are compatible. Namely, we require that the algebraic operations, we have 2 operations, the plus operation, which takes x and y to their sum, and the multiplication by scalars. This is a map from K cross X to X. So these operations should be continuous with respect to our topology. Okay, so these are our objects. Topological vector spaces, well, probably the first example which comes to mind is a norm space. It's a simple exercise to show that if we take a norm space, then the sum operation and the multiplication by scalars are continuous. So norm spaces are topological vector spaces. And of course, there are many other natural examples. We'll discuss them a bit later. It's easy to see that topological vector spaces form a category. And morphisms are, of course, continuous linear maps. So we introduce the following notation. You have 2 topological vector spaces, X and Y. And then the set of all continuous linear operators from X to Y will be denoted like this. This is script L. This is the set of all continuous linear operators from X to Y. In fact, this is not just a set. The axioms of a topological vector space already imply that the topology on X is shift invariant. And this implies the following. First of all, I claim that a linear operator T from x to y is continuous if and only if it is continuous at 0. Or equivalently at any other point. And also this set of xy, the set of all continuous linear operators from x to y, is a vector subspace. Is a vector subspace of the space of all linear operators from x to y. That is, the sum of two continuous linear operators is continuous, and the product of a continuous linear operator by a number is also continuous. This easily follows from the shift invariance of the topology. Okay, it turns out that general topological vector spaces are too general to be interesting. We will be interested in a special class of topological vector spaces. And before we define them, let's recall the definition of a seminorm. So suppose that X is a vector space, and P is a non-negative real function on X. When we say that P is a seminorm, P is a seminorm, if it satisfies the following two conditions. First of all, it satisfies the triangle inequality. This is a triangle inequality. And second, it is homogeneous in the following sense. So we have this identity for all numbers lambda and vectors, all vectors x. So we see that the difference between a seminorm and a norm is that a seminorm is allowed to vanish on non-zero vectors. If we require that P is strictly positive on non-zero vectors, then we get the definition of a norm. And let's also introduce the following notation. If P is a seminorm on a vector space X, then we introduce the so-called open ball, U P epsilon of X. This is a set of all elements Y in our space for which the following inequality holds. So here P is a seminorm, epsilon is a positive number, and X is a fixed vector in our space. We now give the following definition. A polynormed space is a pair consisting of a vector space X. X is a vector space, and P is a family of seminorms. A family of seminorms on X. Let's observe that each polynorm space has a canonical topology. We define, if we have a polynormal space, XP, and then we define the topology on X, the topology on X generated by P, generated by our family of seminorms is the topology which will be denoted by tau of P with the following subbase. So as a subbase, we take the family of all such balls where little p runs over our family big P. So little p runs over our family of seminorms, epsilon over positive numbers, and x runs over our space. So in other words, this is the smallest topology, the weakest topology on X, for which all such open balls are indeed open. So let's recall that to get the whole topology, to get the family of all open sets, we must add finite intersections, first of all, and then arbitrary unions. And then we get the whole topology. Well, of course, if our family P of seminorms consists of a single norm, then we get the usual topology of a norm space generated by our norm. In the case of a norm space, of course, we know that in the case of a norm space, this family of balls is not just a subbase, but is actually a base of the topology. But in the general case, this is only a subbase. If we take the intersection of two such sets, then some bad things can happen if we take balls corresponding to two different seminorms. So in the general case, this is only a subbase. Okay. So each polynorm space has a canonical topology. And now it's natural to conjecture that it will be a topological vector space. And this is indeed the case. The following proposition. If we start with a polynorm space, xp, and equip x with the topology generated by p, then what we get is a topological vector space. So in other words, the algebraic operations are continuous for the topology generated by p. There are several ways of proving this. In my view, the optimal proof is to reduce everything to the case of norm spaces. So I'm assuming we know that this result holds for norm spaces. We know that this is true for norm spaces. No, for if X is a norm space, if big P consists of a single norm, then this is true. This is true for each norm space. So each norm space is a topological vector space. And in fact, the same argument shows that the same is true for seminorm spaces. So if we replace a norm by a seminorm and consider a vector space equipped with one seminorm, then the same proof shows that the operations are continuous. And now, to prove this result for polynorm spaces, we do the following. So for each seminorm P from our family, we denote by IP, we denote by, first of all, XP, the following seminorm space. So we forget about all other seminorms, and we leave only one of them, a little p. So this is a seminorm space. And we let little ip denote the map from X to XP, which is the identity map in the set theoretic sense. but only in the set theoretic sense, because as a topological spaces, these two spaces are different. Here we have the topology generated by all semi-norms from our family, and here we have the topology generated by only one of them. So what can we say about this map? Well, let's observe the following. First of all, this map is continuous by the very definition of our topology. And moreover, property 2, if we have an arbitrary topological space, Y, if Y is a topological space, and F is a map from Y to X, then F is continuous, if and only if IP composed with F is continuous for all P. And again, this is immediate from the definition, because F is continuous if and only if the preimage of any open set from the subbase, that is, the preimage of each such ball, is open in Y. But this means exactly that this composition is continuous for all P. So in other words, in the language of general topology, this means that the topology on X is the initial topology generated by the family of all such maps IP. And this gives us the following. Let's, for example, prove the continuity of the multiplication by scalars on X. Okay, so we have the following commutative diagram. This is our map, mu. So we want to prove the continuity of this map. And to prove the continuity of this map, we look at the following diagram. The following diagram, this is XP, this is XP, this is IP, this is the identity map multiplied by IP, and this is the multiplication by scalars on XP. Clearly, the diagram is commutative. And now we use this fact. So this map is continuous if and only if this composition is continuous for all P. But it is continuous because the diagram is commutative and because these two errors are continuous. So this implies that mu is continuous. And a similar argument shows that the sum operation is also continuous. And this completes the proof. So we see that each polynomial space becomes a topological vector space in a canonical way. And it is exactly this kind of topological vector spaces that we are mostly interested in. So now our first goal will be to give a geometric characterizations of such spaces, of those topological vector spaces whose topology can be generated by a family of semi-norms. Before we can do it, let's recall some definitions from general topology. So suppose that X is a topological space, and little x is a point in our space. Definition 1, suppose that we have a family beta x of neighborhoods of X. And we say that this family is a base of neighborhoods of X, or shortly just base at X. if the following condition holds, if for each neighborhood U of X, there is another neighborhood from this family, neighborhood V from this family, such that V is contained in U. So a typical example is if we take a metric space and a point in the space, and the family of all open balls with a fixed center is a base of neighborhoods of this point. And definition 2, a family sigma x of neighborhoods of X is a subbase of neighborhoods of X, or a subbase at X, if it becomes a base after adding arbitrary finite intersections. If this family, which consists of all finite intersections of sets from sigma x, is a base of neighborhoods of X. Okay, so now let's come back to polynomial spaces and let's introduce some more notation. Suppose that we have a polynomial space, XP. Suppose that little x is a point in our space, and let's take finitely many semi-norms, P1 to Pn, in our family, and the positive number epsilon. Then we denote by U P1 to Pn, epsilon of x, the intersection of the respective open balls, U Pi epsilon of x. So explicitly, this set consists of all elements y in our space, such that this inequality, Pi of y minus x is less than epsilon, holds for all y, for all I from 1 to n. So this is the finite intersection of balls with the same center of the same radius, but corresponding to different semi-norms. We have the following simple proposition. Again, if we start with a polynomial space, then, and we take a point in our space, then the family of all open balls centered at X is a subbase of neighborhoods of X. And second, if we consider sets of this form, U P1, Pn, epsilon of x, where P1 to Pn are semi-norms from our family and epsilon is a positive number, then the family of all such sets is a base of neighborhoods of X. The proof is a simple exercise for you. Well, only little point is that maybe this is not absolutely immediate from the definition, because if we take the definition formally, then to get a subbase of neighborhoods for a fixed point, we must consider, we must take the family of all subbasic sets, that is, of all open balls that contain our point x, but not necessarily as the center. Nevertheless, the triangle inequality easily shows that we can always find a smaller open ball, which is contained in the bigger one, and for which x is the center. And this picture shows that to get a subbase of neighborhoods, it's enough to consider only those open balls for which x is the center. That's the idea. Okay, so now we give the following definition. Suppose that we have a topological vector space X, a topological vector space X. We say that X is locally convex. Locally convex. If X has a base of convex neighborhoods of 0. And we will use the following standard abbreviation. So by definition, a locally convex space, LCS for short, is a short name for locally convex topological vector spaces. Locally convex topological vector space. So the phrase locally convex topological vector space is too long. It's not very convenient, so usually people say just locally convex space, assuming that they are topological vector spaces. Okay, how about examples of such spaces? Why are they interesting? Well, let's look at this proposition. So clearly, the triangle inequality implies that each such ball is convex. And clearly, the finite intersection, actually any intersection of convex sets is convex. So this is also convex. And so we see that each polynorm space, we might start with a polynorm space and equip it with the topology generated by our family of seminorms, then we get a locally convex space. If X is a polynorm space, then X, together with the topology generated by P, is a locally convex space. And it turns out that the converse is also true. We have the following theorem. If we have a topological vector space, X with topology 2, then the space is locally convex. If and only if there exists a family of seminorms, a family P of seminorms on X, which generates the topology tau. So the topology on a topological vector space is locally convex, if and only if it is generated by a family of seminorms. I'll give you a sketch of proof So the details will be exercises for you. So first of all, we start with a base of convex neighborhoods of 0. So suppose that Ui is a base of convex neighborhoods of 0. So the first step is to modify this base in the following way. Let's denote by D the closed unit disk or the closed interval that depends on our base field. In our base field, of course, D is the aberration for disk, because my favorite field is the field of complex numbers, so I denote it by D. But of course, in the case of real numbers, this will be just the closed interval from -1 to 1. And let's observe the following. For each I, there is another neighborhood of 0, denoted by Vi, neighborhood of 0, such that the product of D and Vi is contained in Ui. This follows from the continuity of multiplication. So first we find a neighborhood of 0 in K and in X, such that the product is contained in Ui. And then we just dilate them in a suitable way. So we multiply a neighborhood of 0 on the complex plane in such a way that it is bigger or equal to the disk, and then divide the respective neighborhood in X by the same number, and we get the I. So this follows from the continuity of the multiplication. Okay, and now let Wi denote the convex hull of this set dVi. So this separation means convex hull. The set of all convex combinations in the set. It's the smallest convex set which contains this one. So now a little exercise is to show that Wi is still a convex neighborhood of 0, is a convex neighborhood of 0. Clearly it is convex, so the point is that it is also a neighborhood of 0. By construction, it is contained in Ui, and it has the following extra property, which is useful for us. It is stable under multiplication by D. It is stable under multiplication by numbers in the disk. This is quite useful. Okay, if we now replace each Ui by Wi, then we still have a base of convex neighborhoods of 0. So the family Wi is also a base of neighborhoods of 0. Because Wi is contained in Ui. But this base is better because of this property. Such sets are sometimes called circled sets or balanced sets. So each Wi is not only convex, but is also balanced. Okay, and now we can construct our family of semi-norms. So for each I, I'll let a little pi denote the following function on X. Pi is given by the following formula. This is the infimum of all non-negative numbers lambda for which x sits in lambda wi. This is the so-called Minkowski functional of wi. By the way, why is it finite? It is finite because, again, by the continuity of multiplication. So if multiply x by a small number, then the result will be in wi. So in other words, x will be in lambda wi if lambda is big enough. Okay, so now another exercise. First of all, I claim that Pi is a seminorm. A hint is that the triangle inequality follows from the assumption that Wi is convex, and it is homogeneous because of this. The second part is to show that if we take the open unit ball corresponding to Pi, that is the open ball of radius 1 centered at 0, then what we get is nothing but Wi. This also can be deduced from the definition of the Minkowski functional. And finally, part 3, which is actually immediate from 2, the topology tau is generated by the family of all these seminorms, that is, of all Minkowski functionals of our base Wi. This follows from part 2 and from the fact that Wi form a base of neighborhoods of 0. So modulo these exercises, this completes the proof. So we see that each locally convex topology on a vector space is generated by a family of seminorms. And let's introduce the following terminology. So each such family P is called a generating family. Or a defining family, or a fundamental family. Of seminorms on X. Of course, I don't claim that it is unique. It is not unique. For example, we can multiply each seminorm by 2. And in general, we get a new family which generates the same topology. Okay, so we will be mostly interested in locally convex spaces, or equivalently, in those topological vector spaces whose topology can be generated by a family of seminorms. So we see that polynorm spaces are related to locally convex spaces in about the same way as metric spaces are related to metrizable topological spaces. Well, formally, of course, the structure of a polynorm space is essentially richer than the structure of the corresponding locally convex space, because the same topology can be generated by many different families of seminorms. But in practice, it turns out that when we work with locally convex spaces, with polynorm spaces, the concrete family of seminorms is not so important. What is important is the topology generated by this family. And probably this is the main reason why the notion of a polynorm space is not so much in use, while locally convex, the notion of a locally convex space is absolutely standard and common. And so I will follow the tradition, and I will never use the notion of a polynorm space anymore. But this theorem, that is the fact that each locally convex space is polynormable in the sense that its topology is generated by a family of semi-norms. This fact is very important, and we will constantly use it. So a nice feature of locally convex spaces is that we have two languages at our disposal, two equivalent languages: the language of the topological language of neighborhoods of 0, and the equivalent language of semi-norms. And two languages are always better than one. So let's give just two illustrations of this principle. For example, suppose that we have a local convex space, and suppose that big P is any generating family of semi-norms on X. Natural question: when is this space Hausdorff? And this is a criterion in terms of semi-norms. It is Hausdorff if and only if for each non-zero element in our space there is a semi-norm in our family such that the semi-norm is strictly positive on X. Well, the proof is very easy. For example, if it is Hausdorff, then if we assume for a moment that there is no such P, and if we recall the definition of the topology generated by our family of semi-norms. So if there is no such P, so all P of X are 0, this implies that this element X belongs to each neighborhood of 0. If not, then X belongs to each neighborhood of 0. And of course, this implies that the space is not Hausdorff. And to prove the right to left implication, we do the following. We take two different points, X and Y, and find a semi-norm which doesn't vanish on X minus Y. Let's denote this number by D. So D is strictly positive. Then the triangle inequality easily implies that if we take the balls of radius d divided by d over 2 corresponding to P and centered at X and Y, then they are disjoint. This follows from the triangle inequality. And that's it. So this shows that our space is Hausdorff. Another illustration of the same principle, I mean the principle that many topological properties of locally convex spaces are easily described in the language of semi-norms. So suppose that we have a sequence xn, then it converges to a point X with respect to the topology generated by P, even only if it converges with respect to each semi-norm from this family. So for each little p, P of xn minus X goes to 0. The proof is a simple exercise for you. So everything easily follows from the definition of our topology. Okay, so let's now look at some examples of locally convex spaces. Example 1. Example 1 is a space of all functions on an arbitrary set X. K to the power X is a set of all functions, a space of all functions on X with values in our base field. And X is an arbitrary set. So the natural topology on the space is given by the following family of seminorms. For each point X in our set, we define a seminorm. We'll denote it in the following way. This is a seminorm on K to the power X as follows. If we apply it to a function f, then this will be just the absolute value of f of x. Clearly, this is a seminorm. And of course, it's not a norm unless the set x consists of a single point. So the resulting family of seminorms generates a locally convex topology on K to the power x. And this topology is called the topology of pointwise convergence. Topology of pointwise convergence. On K to the power x. Why is it so called? Well, it is so called if we look here. If we look here, then we see that a sequence Fn converges to a function f with respect to this topology, even only if it converges pointwise. In fact, it's a simple exercise for you to show that this topology is nothing but the product topology. The topology of pointwise convergence, defined in this way, is the same as the product topology on K to the power x. Okay, example 2. Let's now look at the space of continuous functions. So, of course, we know that the space of continuous functions on a compact topological space is a norm space, and in fact, is a Banach space. But let's now take an arbitrary topological space. And let's consider the space C of x, where x is a topological space. In this case, if x is not compact, then this space is not a norm space, but it has a canonical locally convex topology generated by the following family of seminorms. So for each compact set, each compact subset K of x, we define a seminorm indexed by K on C of x by the following formula. So this will be the supremum over K. So K is compact, and so the supremum is finite. And clearly this is a seminorm on C of x. So if we now consider all seminorms of this form, so corresponding to all compact subsets of x, then this family generates a locally convex topology, which is called the topology of compact convergence. The topology of compact convergence. on CLX. Well, again, if we look at this proposition, we see that the convergence with respect to this topology is the uniform convergence on all compact sets. So Fn converges to F in CLX if and only if it converges uniformly on each compact set K. In fact, this topology is a special case of the so-called compact open topology. So here we speak of functions with values in the base field, but if we consider two topological spaces x and y, then this example can be generalized to give the so-called compact open topology on the space of continuous maps from x to y. Example 3, let's now look at the space of smooth functions. For simplicity, let's consider first the space of smooth functions on a closed interval, AB. So the canonical topology on the space is defined as follows. So for each non-zero, bi-non-zero, possibly zero, for each non-negative integer n, including 0, we define a seminorm on our space as follows. This will be the supremum of the nth derivative over the interval. So if n is 0, then this is just the usual supremum norm. If n is positive, then this is a seminorm. And by definition, the standard topology on the space of smooth functions is the locally convex topology determined by the family of all such seminorms. Again, the convergence is easily described. So a sequence that's denoted by Fk converges to F in this space, even only if it converges uniformly with all derivatives. So this is the topology of uniform convergence with all derivatives. Example 4. Let's now take the space of smooth functions on an open subset of Rn. C infinity of U, where U is an open subset of Rn. In some sense, this is a combination of two previous examples. So to define the canonical topology, it's convenient to use the standard multi-index notation. So you have a multi-index that is an n tuple of non-negative integers, alpha n to alpha n. And a smooth function f on U, we denote by d alpha f the respective partial derivative of f. Corresponding to this multi-index. Now, for each compact subset K of U, and for each multi-index alpha, we define a seminorm indexed by K and alpha. This is a seminorm on the space of smooth functions. And this will be the supremum over K, of the respective partial derivative, d alpha f of x. And if we look at all such seminorms, then they generate the standard topology on C infinity of U. The standard topology on C infinity of U is a locally convex topology generated by the family of all such seminorms. So here K runs over the family of all compact subsets of U, and alpha runs over all multi-indices. Again, it's very easy to describe the convergence. So a sequence Fk converges to F for this topology in the space C infinity of U. If and only if it converges uniformly on each compact subset with all partial derivatives. D alpha Fk converges uniformly to d alpha of f over big K for each compact set big K in U. This is the standard convergence in C infinity of U. A good exercise is to generalize examples 3 and 4 to an arbitrary smooth manifold. And to define a canonical topology on the space of smooth functions on a manifold. Okay, example 5. Example 5 is the so-called Schwarz space, which plays an important role in mathematical physics in particular, but not only, of course, in the representation theory also, and in many other areas. The Schwarz space on Rn is the following space. It's denoted by script S of Rn, and it consists of those smooth functions on Rn such that for each pair of multi-indices alpha and beta, the function x to the power alpha d beta f of x is bounded on Rn. So here d beta is the respective partial derivative, and x alpha denotes the respective monomial. In other words, this is the space of those small functions whose partial derivatives decay at infinity faster than 1 over each polynomial. This is a Schwarz space. The canonical topology on the space is again given by a family of seminorms. Well, I use the same notation as here. We just take the partial derivative.
But beta is a number.
Beta is a multi-index. Alpha is a multi-index and beta is a multi-index. So we define a family of seminorms as follows. So for each pair of multi-indices, alpha and beta, we define a seminorm indexed by alpha and beta on a Schwarz space by the following formula. So this will be just the supremum of this function over Rn. And by definition, the standard topology on the Schwarz space is the locally convex topology generated by a family of all such seminorms. In some cases, it's more convenient to take a slightly different family of seminorms. So several families with this property will be discussed will be given in exercise sheets, in our next exercise sheet. But maybe this is the simplest one. Okay. Probably that's all I wanted to tell you about examples. Later we will see some more examples of topological vector spaces which are convenient for different problems. In particular, we see that if we take the space of bounded linear operators on the Hilbert space, then of course this space B of H is a Banach space. But it also carries several useful locally convex topologies. Well, this will be discussed later. And our next goal is to prove a useful continuity criterion for a seminorm on a locally convex space and for a linear operator between two locally convex spaces. So first of all, let's introduce some notation. Suppose that X is a vector space and P is a seminorm on X. We denote by UP the open unit ball with respect to P centered at 0. So this is the set of all X satisfying the following inequality. In some sense, this open ball generates all other open balls corresponding to P because, so we observe that if I take UP epsilon of X, this is nothing but the following set. So we take the open unit ball, multiply it by epsilon, and then shift by X. Okay, we now have two seminorms. So suppose that we have two seminorms P and Q. On X. And we can always take their pointwise maximum. We denote by max of P and Q the function on X which takes each point X to the pointwise maximum of P and Q, P of X and Q of X. We have the following simple lemma. First of all, I claim that this maximum is a seminorm. The maximum of two seminorms is a seminorm. Second, the open unit ball corresponding to this maximum seminorm is the intersection of UP and UQ. And part 3, we have the following equivalence. Q is less than or equal to P if and only if UP is contained in UQ. Well, there's almost nothing to prove here. Part 1 is more or less clear. And 2 is also clear. And also it's obvious that, well, the left to right implication is obvious. If Q is less than or equal to P, and if P of x is less than 1, then Q of x is also less than 1. So the left to right implication in part 3 is also clear. So the only little thing that we have to prove is the right to left implication. But this is also quite easy. We take an arbitrary vector in x. So we want to show that QS is less than or equal to P of x. So we do the following trick. We take an arbitrary positive epsilon, and we observe that x divided by P of x plus epsilon sits in UP. Because if we apply P to this element, the result will be strictly smaller than 1. But by assumption, UP is contained in UQ. So if we apply Q to this vector, the result will be less than 1. Or equivalently, this means that Q of x is less than P of x plus epsilon. And since epsilon was arbitrary, this implies that Q of x is less than or equal to P of x. Okay, that's it. We now have the following continuity criterion for a seminorm on a locally convex space. So suppose that we have a locally convex space X with a topology generated by a family of seminorms P. This is a locally convex space, and big P is a family of seminorms, is a generating family of seminorms on the space. And suppose that Q is a seminorm on X. It is just a seminorm. I don't assume that it belongs to the family P. Then the following conditions are equivalent. Following conditions are equivalent. Condition 1, Q is continuous. Condition 2, Q is continuous at 0. Condition 3, the open unit ball corresponding to Q is open in this topology, tau of P. And finally, condition 4, there exists a finite family of seminorms in P and a positive constant C, such that for each x, we have the following inequality. Q of x is less than or equal to C multiplied by the maximum of Pi of x. So a seminorm is continuous if and only if it is dominated in this sense, but by finitely many seminorms in P. Okay, so let's prove that these conditions are equivalent. First of all, let's show that 1 implies 3. This is immediate because UQ is nothing but the preimage of the following half interval. And this half interval is an open subset of the half line from 0 to infinity. And the preimage of an open set is open. Okay, let's now show that 3 implies 2. So we suppose that this ball is open, and we want to show that Q is continuous at 0. This is also very easy. To show that Q is continuous at 0, it's enough to show that the preimage of each such half interval from 0 to epsilon is open. But it is open because this is nothing but epsilon multiplied by UQ. So UQ is open, and so this set is also open. This shows that 3 implies 2. Okay, let's now prove that 2 implies 4. Two implies 4. We assume that Q is continuous at 0. And we want to show that Q is dominated by finitely many seminorms from P. Okay. Since Q is continuous at 0, we can find a basic neighborhood of 0 such that Q takes this neighborhood to the interval 0, 1, to the half interval 0, 1. And the basic neighborhood of 0 is given by finitely many seminorms and a positive epsilon. So there exist finitely many seminorms, P1, Pn in our family, and there exists a positive epsilon such that we have the following inclusion. This follows from the continuity at 0. For convenience, let P denote this maximum, the maximum of the families of the seminorms Pi from 1 to n. And let's observe that this inclusion means the following. So this means that Q takes U P epsilon of 0 to the half interval 0, 1. Or equivalently, this means that U P epsilon of 0 is contained in UQ. So if we take a vector here, say a little x, then Q of little x is less than 1. But this means exactly that little x sits in this ball. And finally, let's observe that the left-hand side here is nothing but the unit ball corresponding to the seminorm epsilon inverse P. So P of x is less than epsilon if and only if this number applied to x is less than 1. So this ball is contained in this ball. And by our lemma, this is equivalent to the inequality Q is less than or equal to epsilon inverse P. And that's it. This is exactly our condition for it. C is epsilon inverse, and this is P, little p. Okay. Finally, we have to show that 4 implies 1. 4 implies 1. So we take a point, a little x, in our space. So we want to show that Q is continuous at x. So we find P1 to Pn and C as in condition 4. So we take a point. We let P denote this finite maximum of Pi from 1 to n. And let's calculate Q of y minus Q of x. So we want to show that this is small if y sits in a suitable neighborhood of x. Well, first we apply the triangle inequality, which implies that this is less than or equal to Q of y minus x. And by assumption, Q is less than or equal to C multiplied by P. So this will be less than epsilon whenever y sits in the following neighborhood of x. Well, if y sits in here, then P of y minus x is less than C multiplied by epsilon. And so Q of y minus x is less than, P over C of y minus x is less than CP. CP. Cp of y minus x is less than epsilon, then P of y minus x is less than epsilon over C. And by this, Q of y minus x is less than epsilon. Okay. This shows that Q is continuous and completes the proof. And now as a nice corollary, it's time to finish, but if you don't mind, the proof is just a couple of lines. The result is very important. Well, okay. Maybe. Well, at least I formulated because so that you will be able to do the exercises. It's very easy indeed. Useful and easy. The continuity criterion for a linear operator between locally convex spaces. So we have the following theorem, which is actually a corollary of the previous theorem, theorem 2. Suppose we have two locally convex spaces, x and y. So big P is a defining family of seminorms on x, and Q is a defining family of seminorms on y. And suppose that T is a linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is continuous. Condition 2, for each seminorm Q from the second family, big Q, the composition of Q and T, so this is a function from x to the non-negative numbers, is continuous. And condition 3, which is maybe the main continuity criterion, for each seminorm Q in the second family, there exists a constant C And there exists a finite family, Q1 to Qn, of seminorms from big Q, such that the following inequality holds. Q of T of x is less than or equal to C multiplied by the maximum of Pi of x. And this holds for all x in our space. Oh, thank you, of course. Let's call them P1 to Pn, because they are from P. They are from P, of course. P1 to Pn. So for each seminorm from here, there exist finitely many seminorms from here, and the constant such that this inequality holds. So this is an extension of the well-known continuity criterion for linear operator between norm spaces. Because in the case of norm spaces, this condition means just that there is a constant C such that the norm of T of x is less than or equal to C multiplied by the norm of x. So this means that the operator T is bounded in the case of norm spaces. And in the case of locally convex spaces, we have this generalization. Before we prove it, let's look once again to the previous theorem. So I forgot to mention an obvious but useful corollary, which states that each seminorm from the same family P is continuous with respect to tau of P. Maybe this is not entirely obvious from the definition, but this is true because of this theorem. Clearly, if Q sits on P, that it satisfies condition 4 because it is dominated by itself. So now it's easy to prove theorem 2. To prove the equivalence between 2 and 3, we apply theorem 1 to this function. So Q composed with T. This is a seminorm on X. And if we apply theorem 1 to this seminorm, we get that 2 is equivalent to 3. The implication 1 implies 2 follows from the previous corollary. So by the previous corollary, little q is continuous on Y. So if T is continuous, then of course the composition of two continuous maps is continuous. And finally, we prove that 2 implies 1. Again, by theorem 1, condition 2 means that this open ball corresponding to the seminorm is open in the topology tau of P. So this implies that since it contains 0, this implies that there is a neighborhood of 0 I'll say V such that well, it's itself V, so it is open in this topology, and we want to show that T is continuous. Well, let's try to understand together that this is almost obvious. So this set is open we want to show that this implies that t is continuous at 0. Well, why is it so? Well, it seems that this is true, because if x isn't here, then q of t of x is less than 1. So if you apply t to x, then t of x will be in here, because q of t of x is less than 1. So this is true for each q. And since uq is almost a typical neighborhood from a subbase of neighborhoods of 0 in Y, well, why I say almost? Well, it's almost a typical neighborhood of 0 because to get an arbitrary subbasic neighborhood of 0, we must multiply it by a positive epsilon. Well, but by linearity of t, we can do it. So this implies that for each positive epsilon, t takes this set to u q epsilon of 0. And this is a neighborhood of 0 belonging to the standard subbase of neighborhoods of 0. This is a neighborhood of 0 in x. So this inclusion implies that t is continuous at 0. But we already know that a linear operator is continuous at 0 if and only if it is continuous. So this implies the continuity of t. And this completes the proof. So we see that all three conditions are equivalent. No?
You show that if it takes a neighborhood of 0, then t of neighborhood of 0 is inside of a neighborhood of 0. Is it true? Or is it some other thing?
At this point, we don't know that t is continuous. We want to prove that t is continuous. And to prove that t is continuous, we must show that for each neighborhood of 0 in here, there is a neighborhood of 0 in here, such that t takes this neighborhood somewhere here to a subset of this neighborhood. This is just the definition of the continuity at a single point. So for each neighborhood of 0 here, there is a neighborhood of 0 here, such that t takes this one inside this one. And this is exactly what we have shown. This is for this neighborhood of 0 in Y, we see that this inclusion is trivial, but we already know that this set is open. So it's a neighborhood of 0 in x. And so this implies the continuity at 0.
So we don't have to show that the pre-image of an open neighborhood.
No. The continuity at a point, at a single point. This is just, well, let's recall the definition from general topology. If you have two topological spaces, x and y, and the point little x in big X, and the map from x to y, then we say that f is continuous at this point, if and only if for each neighborhood u of x, there is a neighborhood v, or u of f of x, there is a neighborhood v of x, such that f of v is contained in u. And this is exactly what we have shown. We have shown t is continuous at 0, but we already know that for linear operators between arbitrary topological vector spaces, the continuity at 0 implies the continuity. Okay, so that's all for today. At the next lecture, we apply this result to to the study of equivalent families of seminorms on the same vector space. And we will understand why locally convex spaces are better than arbitrary topological vector spaces. Thank you.